Hello and welcome to LFI Educates. Today we are going to continue this laws of motion. The topic that we are going to study today is about friction. Friction is a force that opposes the relative motion between two surfaces in contact. I'll write down here. Friction is a force that opposes the relative motion between two bodies or two surfaces in contact and acts tangentially to the surface, and it always, the force of friction is always opposite to the direction of the applied force. If the surface is rough like this, now when a body is sliding, the force of friction, suppose a body is sliding here on the rough surface, suppose this is your object, you are applying force in this direction, the frictional force will act tangentially like this, tangent to the curve. It will act always tangentially and it will be opposite to the direction of the applied force. So whenever one body tries to move on the surface of another body, both the bodies will overcome frictional forces. They will overcome frictional force, that opposing force. The one body will not allow the other body to slide freely, and this body will not allow this body to slide freely or to move freely. That opposing force, we call it as force of friction, or simply we call it as friction. There are three types of friction. Types of friction, let us see. The first one, we call it as static friction. It is that force of friction which is exactly equal to the applied force. When a body is at rest, suppose this is the surface, there you are going to move this body. When this body is at rest, the body of mass m, it does not have any friction. It does not have any static friction. The moment you try to apply force here, suppose say 1 Newton of force I have applied, then the body does not move. The moment we apply force, the friction provided by this surface to this body will be called as static friction. When no one is applying force or there is no external force, then there is no static friction. Once you start applying the force, then only the static friction will come into play. This side will be your static friction. We write it as Fs in the opposite direction. If you go on increasing this force of friction from 1 Newton, suppose you are applying now 2 Newton of force, then also the body may not move. Then this static friction also will become exactly equal to 2 Newton. They both will be equal to each other. Now if I apply suppose 3 Newton of force, then also the body does not move. Then the force of static friction also will be 3 Newton. Suppose I am going to increase the force. At 4 Newton of force, the body tends to move, about to move or start sliding. Then at that time, the force of static friction also will be 4 Newton, and at that stage we will say the maximum static friction. The static friction started from 1 Newton, 2 Newton, 3 Newton, now became 4 Newton. So 4 Newton is the maximum static friction, and maximum static friction we call it as limiting friction as well. We'll call it as limiting friction. So maximum static friction is known as limiting friction. Now if I apply 5 Newton of force, then this friction will not be called as static friction. Then to come to the second category, that is called kinetic friction. The second friction is your kinetic friction. We write it as Fk. The force of friction that comes into play when a body actually moves over the surface of another body, that time the friction we call it as kinetic friction. When a body starts to move, suppose this is your body, applying force and started to move in this direction, and the friction provided by this surface in the other direction, opposite direction to the applied force, that force of friction we call it as kinetic friction. Now to see graphically how it looks when the body is at rest and when it is in motion, this is the applied force along x-axis. And this is your force of friction, suppose representing by y-axis. Force of friction. Initially, to make a body to move, the applied force must be more, then only it starts to move. We have come to know from the case of limiting friction. So when you go on applying the force, the body does not move, does not move, does not move. You are applying force, increasing, and then the static friction also becoming more and going higher up. Then it reaches the highest value. The highest value means we call it as limiting friction. We write it as FL also. Limiting friction. That means from this point O to point A, the body is at rest, did not move. To overcome inertia of rest, you have to apply more force. The moment you reach this limiting friction, the body starts to move. That time, the force of friction provided by the surface will become less, it will come down, and then it will become easy to move. This part represents the motion of the object. In this portion, the friction provided by the surface to the body, we will call it as force of kinetic friction. Graphically, you can represent this way. Here you can see, to overcome the inertia of rest, you have to apply large force. After that, once it reaches that stage, you don't have to apply more force at all. It smoothly will move. That you might have come across while riding a bicycle. The first pedal you have to give it more force, then only you can balance your body. After that, once the wheel starts to revolve, then the cycle becomes steady. You don't have to apply much force. With less force also, it will just go on moving. Like vehicles and all, also first you have to start with number 1 gear, then 2, 3, 4, and so on. It goes on increasing. Starting, it requires more force. Then the object starts to move. And the third type of friction, we call it as rolling friction. In rolling friction, is a frictional force that is provided by the surface to an object if it is in rolling motion. Suppose it's an inclined plane and this marker is rolling on top of it. Then my hand, how much friction it will provide to the marker in the opposite direction, that will be called as a rolling friction. These are the 2 types of friction. Now let us study about coefficient of friction. There are 2 types of coefficient of friction. The first one is called coefficient of static friction. We write it as mu s. It has been found out that the force of static friction is directly proportional to the normal reaction. Here R is normal reaction. R is normal reaction. We can use capital N also, or we can use it as R. Now to remove this proportional sign, the force of static friction is equal to K. R will come, or the letter that we use here is static coefficient of static friction mu s R. It's equation number 1. So mu s, the coefficient of static friction, is defined as the ratio between the force of static friction divided by the normal reaction R. Coefficient of static friction is defined as the force of static friction divided by a normal reaction, or you can even write this ratio of force of static friction to its normal reaction, defined as the force of static friction divided by normal reaction. It does not have any unit because it is a ratio term. Both the units are Newton, it will get cancelled. But here one more thing is there. Equation 1 is valid only when the force of static friction has its maximum value, that means limiting friction. Equation 1 is valid only when the force of static friction is maximum, that means it is in terms of limiting friction. Or else, what equation we can use here is, general equation will be using like this: force of static friction, if it is not the limiting friction, then it will be always less than or equal to the coefficient of static friction into normal reaction. This is the general formula you will be using it. Always the force of static friction will be less than the normal reaction and the coefficient of static friction. Coefficient of kinetic friction we write as mu k, and here also it goes the same way. The force of kinetic friction Fk is directly proportional to the normal reaction R. So Fk is equal to mu k into R, where mu k, the coefficient of kinetic friction, will be force of kinetic friction divided by normal reaction R. In this case, it will be always equal, both will be equal to each other. In this case, we can define like this: coefficient of mu k is defined as force of kinetic friction divided by normal reaction. So you will get like this: mu k is equal to Fk divided by R. Here also it does not have any unit because it is a ratio term. Both are forces. Newton will get cancelled. I am writing fully in scalar form because these are all vector quantities. If you put arrowhead, you can put it at your desired will. Here, one important thing to note is that mu k, the coefficient of kinetic friction, is always less than the coefficient of static friction. This is because once the body starts to move, then the force required to make the body to move becomes less. That's why the coefficient of kinetic friction is always less than the coefficient of static friction. To overcome inertia, we have said that initially we have to apply large force. Once the body starts to move, it moves smoothly. With less force also it can move. So mu k will be always less than mu s. Now let us study about the motion in an inclined plane. Motion in an inclined plane. Let us consider a body of mass m at rest on an inclined plane we will take it like this. This is your incline, suppose this is a horizontal, and this is your inclination. It's inclined at an angle, say theta. If I keep one body here on an inclined plane of mass m, then the various forces that will act on this body, the various forces acting on the body are, number one, the weight of the body. This is the ground level. The weight will be acting in the downward direction. The forces I am marking with blue colored ink. This is the weight of the body, that is mg, acting towards the ground. The other force that will act on it is the force of static friction. We write it as Fs. And the third force that acts on the body is a normal reaction, that is, we are writing it as R. This normal reaction must be perpendicular to the inclination. Must be perpendicular to the inclination. This is your inclination. I am darkening it. These are the three forces that are acting on the body, and the body is of mass m. Now, number one, the weight mg acting downwards. The second force that is acting on the body is the normal reaction. That is R. Perpendicular to the plane. And the third force that is acting is the force of static friction. Here we are writing it as Fs, that is, better write in scalar form only, friction Fs parallel to the plane. Now, we'll resolve it into the rectangular components. Here mg, these two are perpendicular and parallel to the plane, but this one is neither parallel nor perpendicular to the plane. So this mg, weight mg, we can resolve it into its two components, one parallel to the plane and one perpendicular to the plane. If this angle is theta, this angle also will be theta. This angle will be theta. How it will be theta? You can look here. If I increase this line, this is 90 degree. Then this is theta. Then this is 90 minus theta. Here it is 90 minus theta. This is perpendicular here again. So 90 fully, it is 90 minus, this is 90 minus theta. You will get 90 degree minus 90 degree minus is plus theta. So it will come out as theta. This angle will be theta. So if you resolve it into its rectangular components, then this forms the base of the right triangle. This one, if you drop one perpendicular here, this will be the base. So this will be mg cos theta. This will be mg cos theta, and ultimately the other side will be mg sin theta. So you resolve it like this. So on resolving, mg into its rectangular components, the first one mg sin theta perpendicular to the plane. And the second one mg cos theta, mg cos theta perpendicular to the plane, and mg sin theta parallel to the plane. Like this we can resolve it. First of all, we have to know the various forces acting on the body. Then we have to know how to resolve, which part to resolve, and why we have resolved. That is also very, very important, because this one is perpendicular to the plane, this is parallel to the plane. Perpendicular and parallel you don't have to resolve. What you have to resolve is the one which is neither parallel nor perpendicular to the plane. So mg, that weight, is neither parallel nor perpendicular to the plane, so we have resolved it, one perpendicular and one parallel. Now what you have to do is, as the body is not moving, it is at rest, this r is equal to mg cos theta. We write here r is equal to, in equilibrium, we write down here, when the body is in equilibrium, r is equal to mg cos theta. Let us mark equation number 1. Or r, normal reaction, you know, when you use coefficient of static friction. Now we cannot use, for time being we'll keep as it is, and because the body is not moving, so static friction will not come into play, we'll keep as it is. Then here Fs will be equal to your mg sin theta. Fs, the force of static friction, is equal to your mg sin theta. This will be equation number 2. On increasing the angle theta, this component, if you increase this angle theta, how will you increase it? This inclination will move little bit like this, then this angle will become more and more. On increasing this angle of inclination theta, the component mg cos sin theta will start increasing because the body will be about to slide. Then when this mg sin theta will increase, this fs, the coefficient of static friction, also will go on increasing because it is a self-adjusting force. Coefficient of static friction is also known as self-adjusting force. The more you increase this force also will go on increasing. And then if it reaches a certain maximum value, that is your limiting friction, then the body will tend to slide. Now when this angle theta, you go on increasing like this, the angle theta will go on increasing. At one stage, the body which is on the incline, which was at rest, will start to slide. When it will start to slide or about to slide, when it will start moving, then this angle theta will be called as angle of repose. So I'll write down here, on increasing the angle theta, the component mg sin theta goes on increasing, and when mg sin theta goes on increasing, the force of static friction also will become more and more. It goes on increasing, as well as the force of static friction also becomes more. Will not allow it to slide. But if you go on increasing further, this angle theta, then this mg will overcome the force of static friction, then will start to slide. But on further increasing theta, the component mg sin theta overcomes the force of static friction, Fs, and the body tends to slide, and the body tends to slide. At that stage, the angle theta will be called as, at this angle theta will be called as angle of repose. So if anybody will ask what is angle of repose, then you will have to say that if the angle of inclination is enough to make the body slide over the surface of an inclined plane, then that angle is known as angle of repose. You can say like this, and it's represented as theta m. Now angle of repose, we write it as theta m. Now here, now the body is moving now. Now it is in motion. Now here if you look, this equation 1 and 2, these were the equations when the body was at rest. From equation 1 and 2, equation 1, normal reaction, you can write it as, you can keep as it is, equation number 1. Equation 2, first let us do Fs. Coefficient of static friction is equal to force of static friction divided by normal reaction R. So here your Fs, you can write it as the product of mu s into R, the coefficient of static friction into normal reaction. So this Fs I am writing first, that is mu s into r, and this is equal to mg sin theta. This is from equation 2. From equation 2. And from equation 1, this is your same thing, r is equal to mg cos theta. This is your equation 1 itself. You may be thinking, why I wrote equation 2 first, but as we are going to divide, sin theta by cos theta gives you tan theta. That's why I wrote first this equation, then I wrote this one. Now, on dividing, this one you can mark it as, or you can write like this on dividing the two equations. You get mu as r divided by r is equal to mg sin theta divided by mg cos theta. And when the body is moving, we said that the angle, we call it as angle of repose. We write it as theta m. So mg if we cancel, r if we cancel, you get a very important relation, that is tan theta m. Tan theta m is equal to this one, sin theta by cos theta is tan theta, and theta m represents angle of repose, that is equal to coefficient of static friction. Sometimes you may be asked to find this relation. The coefficient of static friction is equal to tan of the angle of repose. Tan of the angle of repose is equal to coefficient of static friction. Now, when it tends to slide, now let us see when it really slides, then what will be the acceleration. Let us calculate and see. Now, if the block is sliding down, with acceleration a, suppose now the block is moving freely, then you will not have coefficient static friction, now you will have kinetic friction acting on the other side. So Fs will no longer exist, it will be replaced with Fk. If it is sliding down with acceleration a, then the net force acting on the block is, let us use small letter f, this is indicating the net force. What will be the net force? Let us see. This is mg sin theta, it's coming down, so it will be more, whereas the force of kinetic friction in the other direction will be minus mg sin theta minus Fs will not come, now it will be force of kinetic friction. But we know that the force, if it is F, the acceleration with which it is sliding is A, then by Newton's second law of motion, force is equal to mass into acceleration. We'll put it here like this, mg sin theta minus Fk, force of kinetic friction. If you do like this, force of kinetic friction here, then it is mu k into r. This is mu k into r. And what is r also you know already. Look the diagram. Ma is equal to mg sin theta minus mu k r. The normal reaction is equal to mg cos theta. This is mg cos theta. So m if you take common, g sin theta minus mu k. G is also common, but you can keep as it is, g cos theta. Then here ma. So acceleration with which the block will slide down, the inclined plane is A is equal to G sin theta minus mu K G cos theta. So this is your final expression which the body would slide in an inclined plane. Here what we used, just to remember, Fk we have replaced with mu K into R, and here we have replaced this R as mg cos theta. Mg cos theta. From the diagram it will become clear. So this is the way you can find out the body's acceleration, which it will fall down or slide down in the inclined plane. So we started with the body at rest, and when the body tends to move, the angle of repose came into action. Then after that, if the body continuously moves down, then what will be its acceleration? Three things you have learned here: from the motion of a block or motion of an object in an inclined plane. Thank you and have a nice day. Stay tuned with LFI Educates.